All right, let's talk about something that's, absolutely essential to the modern world, but often goes unnoticed, the servo motor. We're going to pull back the curtain and really demystify how these little powerhouses give us such amazing, precise control.
Have you ever just watched a robotic arm or maybe some complex factory machine and wondered, how in the world does it move so perfectly? How does it stop on a dime exactly where it needs to? Well, the secret sauce behind all that incredible precision is the servo motor.
So, what really makes a servo different from, say, a regular DC motor? Well, think about a simple little motor, right? You give it some juice and whoosh, it just spins and spins. That's its job. A servo, though, that's a whole different ballgame. It's not about endless rotation. It's about getting to a very specific position, a specific angle, and then holding that position rock solid. Okay, so here's what we're going to cover. First, we'll nail down what a servo motor actually is. Then, we'll dive into the secret of how it gets that amazing precision. After that, we'll talk closed loop versus open loop systems, decode what torque really means, and finally, look at how power, speed, and size all play together. So, let's get right to it. At its heart, what is a servo motor? It's basically a brilliant device that takes an electrical signal and turns it into a very specific, very controlled mechanical movement. Remember, the goal here isn't just to spin, it's to command motion with incredible accuracy. And trust me, you've seen these things in action all over the place, probably without even realizing it. They're the muscles that move robotic arms. They're the key to precision in automated factory lines. They're even what gives high-end RC cars that super responsive steering. Their one job is to get something to an exact spot and keep it there, period. Okay, now for the really cool part. What is the secret to their precision? How do these little gadgets pull off such amazing, controlled movements? Here's the big idea. A servo isn't just getting a simple on or off signal. It's receiving a specific coded message from a controller. It's like you're not just telling it to go, you're giving it a precise command, like move to the 90-degree position and hold. The servo understands that command and executes it perfectly. Now, for most standard servos you'll come across, they operate in a 180-degree range, basically a perfect half circle. And what's really interesting is that this limit is often a physical one. There's literally a small pin inside the gearing that physically stops it from rotating any further, which guarantees it stays within its designated range. So that brings us to a really fundamental idea in the world of servos, the difference between what we call closed loop and open loop systems. This is absolutely key to understanding how they really work. The most common type, and the one that gives us the best control, is a closed-loop system. You can almost think of it as a motor with its own little brain. It has an internal feedback system that is constantly asking itself, am I in the right spot? Am I where I'm supposed to be? This constant self-correction is what lets it hit its target and hold it, even if something tries to push it off course. So here's the deal. On one hand, you have closed-loop servos. They have that feedback pin, which gives them incredible control, but it usually limits them to that 180-degree rotation. On the other hand, you have open-loop servos. These can spin a full 360 degrees, which is great. But because they don't have that feedback, they just aren't as accurate for jobs that need that pinpoint positioning. All right, let's talk about those numbers you see printed on the side of a servo. You might see something like 25 kilograms and think, wait, this little thing doesn't weigh 25 kilograms. And you'd be right. That number isn't its weight, it's a measure of its power, a really important spec called torque. So, what is torque exactly? In the simplest terms, it's the rotational force, or the twisting strength of the motor. It tells you how much weight the servo can lift or move when it's attached to a lever at a certain distance from its center. You'll very often see a rating that looks something like this: 25 kilograms centimeters. Okay, cool, but what does that actually mean when you want to make it lift something? Let's break it down. It's actually pretty simple. If you have a lever arm that's just 1 centimeter long, this servo can hold a massive 25 kilograms. But if you double that lever arm to 2 centimeters, its lifting power gets cut in half, down to 12.5 kilograms. Extend it out to 3 centimeters, and it drops again to about 6.25 kilos. The rule is simple. The longer your lever, the less force the servo can apply at the end of it. But of course, torque is only one piece of the puzzle. To really get the full picture of what a servo can do, you have to look at the whole data sheet and see how power, speed, and even its physical size all relate to each other. Now, voltage is a total game changer for a servo's performance. If you run it at a lower voltage, say 4.8 volts, you're going to get lower torque and a slower speed. But if you can feed it more voltage, like 7.2 volts, you suddenly unlock a lot more strength and much faster movement. And the difference is, well, it's pretty dramatic. You can see it right here. That jump in voltage gives you a serious jump in torque. That's the raw power of the motor. It's a direct relationship. More volts equals more power. It's that simple. Okay, let's quickly sum up some key relationships to keep in mind. First, more power usually means a bigger motor. A servo with a high torque rating is generally going to be physically larger. Second, power use changes. The motor uses the most power when it's actively moving, but very little just to hold its position. And finally, and this is super important, if the motor gets blocked and can't move or stalls, the current it draws can skyrocket, and that can easily damage the servo or your other electronics. So you have to be careful about that. So, there you have it. The next time you see a robot moving with that uncanny, graceful precision, you'll know it's not magic. It's just some really clever engineering, packed into a little box called a servo motor, turning simple electrical signals into powerful, precise motion. We've laid out how they work. The only question left is, what are you going to build with them?